Yes, we can. There we go. All right. So, Fisher projection, it can be rotated 180 degrees on the page. Okay, so a Fisher projection can be rotated on the page by 180 degrees. Okay. So let's do an example of what that looks like. So remember our Fisher projection? It looks like a cross, but these are actually bonds with atoms attached to it. Okay. So let's just say our hydrogen's right here, our OH is right there, and at the middle there, what's in the middle? Carbon. The carbon. We just don't show it. Okay. And then the other groups here is a CHO and CH2OH. Okay. All right. Okay. So imagine here we do a 180-degree turn, okay? So a 180-degree turn. So imagine you're taking this square and you're kind of rotating everything by 180 degrees. Okay? So we do a 180-degree turn here. And basically what we're going to see is that the HO is going to be on the opposite side of the H. And the CH2OH is also going to be flipped. Sorry, that's wrong. All right. So if we switch all four places of the substituents at the same time, we don't get a different stereoisomer. It's the same molecule. Okay. So if we were to assign this configuration, one is R, and this one is R as well. Okay. So let's just say it's R. When we do a 180-degree turn, we'll still get the same configuration. Okay. So here we have the same molecule. All right. So I won't go into why this is R yet, because we're gonna get to that step. So let's take it a little bit slower today. Okay. All right. So now, however, if you turn it 90 degrees, you will get the enantiomer. Okay. So let's show an example of that. Okay. So number 2 here. A rotation of 90 degrees, okay, will give the other enantiomer. So in this case, we'll get the mirror image of our starting molecule here. Okay, so let's do an example there. So H, CHO, OH, CH2, OH there. Okay, so say we do a 90-degree turn. So we get HO, CH2, okay. So when we do this, what happens now is that remember the bonds on the vertical line? Those are our dashed bonds, if we remember from last time. Remember? So these is equivalent to this, right? H is right there, OH, and then our wedge bonds here, we have CHO, And over here, let me just erase this a little bit. We have HO, CH2 right there. Okay? So what happens if we now put the groups that were on the wedge bond, now they're on the dash bond. When we swap those two groups, in this case, all four of them kind of went to the opposite bond they were, if we compare it over here. Now when that happens, you get the enantiomer, okay? So in a Fisher projection, if you rotate the groups 90 degrees, and now they're on the opposite axis, going from the vertical to the horizontal, because we defined that as wedge bonds going in the back away from us, or sorry, dash bonds here, and wedge bonds coming out of us, if we switch those two groups to different orientations, we get the other enantiomer, okay? So, yeah.
Sorry, can I clarify when you say the other enantiomer?
Yes.
You mean
This one right here. So let's go. So this one would be R, and this one would be S.
so those are there's only two, right?
Yes, there's only two enantiomers. Yes.
Okay.
So we can actually let's do a little exercise here. Okay, so for this one on the right, let's assign priorities. Remember we assigned priorities last time? So which one of these groups would get the first priority? So let's look at this one right here. All right, so if we look at the carbon atom, right? So this center here is my carbon. Remember, that's my carbon atom. Okay, so we're looking at all the groups around that carbon atom, right? So which one would have the highest priority? Remember, we're looking at the connection to an atom with the highest atomic number. It's the OH, right? Because carbon is number 6. So oxygen is number 8 in the periodic table. So that will take priority. So we could label this OH as A. All right. Now we have to compare the other groups. Well, right away, we can see hydrogen's there, right? What priority would that have? 4, because that's the first atom on our periodic table. It will have the lowest atomic number. So let's put that 4 or letter D, okay? And then, now we have to decide which one of these is second and third. All right. So let's just write to the side here, a CHO group. So this group right here, this looks like a C double bond O and an H. All right. And this group right here, CH2OH, that looks like C, H, and H, OH, right? Okay. So if we compare those two groups, remember, we look at the point of first difference, or where these atoms differ. Okay, so they both have carbon, right? But now one of them, I have 1 H. What about the other one? In the second example, I have a carbon to how many H's? 2, all right? So I already have 2 more H's, whereas my other carbon over here, both of them are attached to oxygen. But what do we treat a double bond as? Yeah, 2 bonds to oxygen. If I have 2 bonds to oxygen, that's going to trump over 1 bond to oxygen. Okay, so it's going to be like that's how we tell the difference. That's where we tell which one is more important than the other when assigning priorities here. All right, so which one would come second or be given letter B? CHO, good. And then this one would be C. Okay, now if we draw our priorities here, we go from A. We don't look at D, right? It's always A to B to C. All right, hydrogen, or the lowest priority group here, will always be given the dash bond or towards the back. So since they're both dash bond, the H has to be just at one of those positions. It doesn't matter, okay? So we go from our A direction to the B direction all the way to the C direction here. And then we go back to A. All right. Now we follow those arrows. What kind of direction do we see? Is it counterclockwise or clockwise? Counterclockwise. Does anyone have any questions how we get counterclockwise? It's like you're making a left-hand turn with a steering wheel. And clockwise would be the opposite direction if we went from A to C to B, but that's not the order, so that's why. And so now this one's S, okay? Now if we look at this one on the right, so this one on the right here, we see that the CHO and the CH2OH, they're on the opposite axes, right? So they have been switched. When you switch those two positions, you get the opposite enantiomer, okay? So this one would be R, okay? So to actually assign R here, we would have to do a little rotation of the groups. And I'm going to do that in my next example, okay? Captain's question.
So if you did give us a Fisher projection, because like with the example of like the R enantiomer, since H is one of the dashes, would we have to do the 90-degree turn to get it to be wedged to then do the?
Yeah, so in this case, we would take this example and we would rotate until the H is now on the vertical.
So anytime we get a Fisher projection with H being on the horizontal.
Yes,
dash,
right, because, yeah, where it's wedged, we need to put it on the dash position. Exactly. Good. Are any other questions about that? We'll do some more examples, okay? But are any more questions before I move on?
Just to clarify what Catherine was saying.
Yes.
The question for me, so the horizontals are always wedged,
Yes. So
the verticals are always down?
yeah. So let me just clarify that. Let's see. Do I have? Okay. Let's see. Let me just exit out here for a sec, and I'm going to go to. All right. Don't look at that. So let's look at our. So this is right? It's on my canvas. So it's a great page if you don't have a model kit to visualize molecules in 3D. Okay. So let's look at methane. I think that will help. Let's see, organic, methane here. Okay. So notice how Fisher projections, doesn't it kind of look like what this is right now, the Fisher projection? We have the vertical line and the horizontal line. You see that? But look at the horizontal. The horizontal bonds, are they coming towards us or away from us? Towards us. That's why we draw the wedge bond. Now, if we look at the vertical bonds, we have to kind of rotate this a bit. If we look at them, are they going away from us or towards us? Away. You see the vertical bonds are pointed towards the plane of the paper. That's away. So that's why we draw Fisher projections like this. It's all based on the orientation of how you view, or perspective of how you view these molecules. All right. Does that make a little more sense? That's why we do two wedge bonds?
Yep.
Okay. Are any other questions about that? We move on. No? Okay. So I'm going to go back here, and then if there's no question about this, I'm just going to hide this layer and add another one. Okay. All right. So now let's go, let's do an example where we look at the Fisher projection, and we want to assign the stereochemistry label, R or S. Remember, those are the two stereoisomers that we could have. So now we go to point number 3 here, okay? All right, so in Fisher projections, you can rotate them, but to rotate them, you have to hold one of the atoms fixed, and you're just going to rotate the other 3 groups around it, okay? So let's do this example. So 3 here can hold one atom fixed, okay, while the other 3 rotate. Okay, so let's just use the example we had before. So it's consistent here. So CHO, CH2OH, then OH here. All right. Okay, so I'm going to show you in two ways. We're going to hold the bottom group fixed, and imagine we're holding something at the bottom fixed, and then we're just rotating the groups at the top like it's a dreidel or something. Like it's like a Ferris wheel. It's going round and round. Okay, so we're going to hold CH2. We're going to hold that in place. Okay, and let's rotate the other groups clockwise. All right, so remember clockwise in your perspective is going this way, so that's going clockwise, okay? So when you say hold there, you're going to hold the CH2, so that position's not going to move at all, okay? And what you're moving are the other atoms in a clockwise direction, okay? So a clockwise direction would be, all right, moving this here, and then moving this over here. Okay, so move all those positions in a clockwise fashion. All right, so where's my H going to be now? Top, okay, good. And then how about the CHO group? Where's that going to be located now? Right or left? To the right. Thank you. All right, so remember the CH2OH, that's what we're holding fixed. So we can only rotate these atoms as long as one point is held constant. All right, and then on the left here, what's on the left now? OH. Okay, good. So here, when you do this, when you rotate three groups around like that, you don't change the stereochemistry, okay? Because you're rotating more than two groups, you're interchanging more than two groups, all right? Two groups is the key here. If it's two groups switched, you're going to change the stereochemistry. If you three or all of them, it doesn't change. That's the rule, okay? And we can verify this by assigning R and S too, okay? So, all right, this one was originally R, so we're just going to say it's R. If we look up the stereochemistry, or, determine it, it'll be R, okay? So let's prove that by assigning the priorities over here. All right, so we already did, right? So H is letter D, CTOH is C, and this is A and B. All right, so when we do this, what's the direction now? When we assign the priorities and we move in the direction from A to B to C, what isomer is it? Is it R clockwise or is it S counterclockwise? R. So remember, you can go over D, but you just have to go in the direction where it's A to B to C and not A to C to D. Okay, it has to go in order. So we do this way, we can go from A to B, B to C, and then C to A. So this looks like in a clockwise arrangement. So this looks clockwise. And it's not clockwise because we rotated clockwise. That's just a coincidence. All right, so you have to do this assignment, okay? So it's R. So notice here the stereochemistry didn't change when we rotate the groups, okay? So I know this seems like a lot. Well, you have to do that on exam. You'll have to be able to do the hang of this, okay, on exam. So if it's not in the right configuration, if the H, the lowest priority substituent, is not on the vertical axis, you will have to rotate it like that, okay? And this is something we train previous students on to do as well. Yeah, Captain.
So when you said if we change two or more groups, it would change the enantiomer?
No, so only if you change only two.
Only two?
Only two, yes.
So
three or more.
Okay,
So we changed the positions of three of them, right, in this one?
Yeah.
Yeah, so that one won't change the stereoisomer. You'll get the same molecule, right? Okay, are there any other questions on this example? So there's a lot of examples that we unfortunately didn't have time to go over last week, but in that lab handout we went over, that's a good way to practice assigning R and S, okay? But any other questions before I move on? No? Okay. So that's it for fit. Oh wait, let's do one more, okay? Let's do the, let's just show that it doesn't matter which direction you rotate it, okay? So let's do the other example here. So let's just redraw what we had. So we have CHO, OH still, right? H, CH2. All right. So my recommendation, when you have to do this, I would pick one of the top, one of the vertical groups and hold that group and rotate it. I wouldn't try to rotate one of the horizontal groups because it may be difficult to rotate around horizontally here, okay? So I would hold one of the vertical groups, either one at the north or the one at the south. I would hold that constant and do your rotations, okay? All right. So in this case, let's do the opposite. We're going to hold CHO this time. And instead of rotating clockwise, we're going to do counterclockwise. Okay? CHO. So let's rotate. Other groups. All right. So in this case, we're holding the top constant, and we're going to rotate the groups in a counterclockwise direction. Okay? So why do you think we don't rotate it clockwise? Would that move the H anywhere different? No, it'll still be on horizontal, right? So it won't do anything for our purposes. So that's why we go counterclockwise. Okay. So let's now do our structure here. HO. All right. So that one was moving counterclockwise. So our OH is now going to go into position where H was. H will now occupy this position. And then the group on the south part will now go towards the east. CHO. All right, H right here. And then CH2, OH. All right, so let's just keep practicing writing our priorities. So that's the way to get the hang of this, okay? So we got D, A, B, and C. Now if we assign priorities again, and now this part will be our loop from A to B to C. All right. Has the stereochemistry changed at all? Has our direction changed from our previous example? No, right? So even though the A's is still in the same place, but you can still see that it's moving in this direction, so it's still going to be R, the R enantiomer. So they're both R in this case. Okay. All right. Any questions? Anyone want me to do another example? We could do another example, or are we okay with this this concept here of rotating? You okay? All right. Okay. All right. Well, I gotta do a new page. I'm gonna do a new one. Boop. Okay. So let me just summarize how we assign R and S in case we need a visual, more kind of tutorial-like example here. All right. So how to assign R, S configurations two Fisher projections. All right, so the procedure here is not that different from how we learned it last time, okay, last class, all right? So you assign priorities to substituents as you normally do, okay? So assign them normally to the groups around the chiral atom, all right? So substituents normally. All right. All right. So, in the Fisher projections, all right, so we wanted to make sure that we rotate the groups. So we place, all right, the lowest priority substituent, so the one that has the fourth designation, or the letter D. That's the lowest priority substituent, all right? Place the lowest priority substituent at the top or bottom. Of the projection. All right, when we do this, this will have the group pointed towards the back. And remember, when we assign R and S, that's how the system was developed. The lowest priority group has to be pointed towards the back, okay? So if we do it this way, the lowest priority group will be oriented towards the back. Away from the observer or viewer. So away from the viewer. Okay? And then lastly, once we have that, our conditions are great for assigning the configuration. So we just determine RS based on the direction of the substituents. Okay? So number 3 here. Determine the order of substituents or groups like we did before. A to B to C, and direction. Okay, and once we do that, we can now assign R or S. So as long as we do that, we can always assign R and S, okay? Okay, so just to reiterate, I'll put an example to you, okay? And then we can go over it together. Whoops, not eraser. All right. So, all right, let's go ahead and assign that stereo center there. So that, let's assign it, is it R or S? All right. Does anyone have an idea of what I should do first? Is hydrogen in the right position? No. So we should do what first? Let's rotate these groups. around one of the vertical atoms. All right, so which atom do you want to hold constant? So let's number them. Letter them, and D. All right, so which one should we hold constant? It actually doesn't matter because one way you'll rotate it a certain direction, and if you hold the other atom, you'll rotate it another direction. Yeah. All right, so let's pick one. We want to hold B constant or C constant? B? All right. Or does anyone want C?
Yeah, let's do C.
All right, let's do C. Okay. Well, we already did, so I'll show you guys. It doesn't actually matter which one you hold constant, okay? So let's do C. All right. Here's B, A, and D, okay? All right. So if I rotate, all right, so there's a certain direction we have to rotate, okay? So let's think about this. So we're going to hold C. All right, we're looking at C, right? H is letter D, and we want letter D to be where letter C is, right? Because we're holding letter B is. We're holding C constant, right? So which way should we go? Clockwise or counterclockwise? Yes, clockwise. Why clockwise? What happens if we go counterclockwise? Where will D end up at?
Where A is.
Where A is, right? It doesn't go where C is because we're rotating around that axis. So it might look like, oh, we can just put where C is, but we're holding C constant, okay? So we have to rotate clockwise. All right. So we're going to rotate D for B, B to A. Then A is going to go where D is, okay? So now let's write the new projection over here. All right, remember C is where we held constant, right? So we don't rotate, we don't change that position. So now where are all the rest of the letters? Let's start with letter A first. Where's that? To the left. All right. Okay, where was hydrogen or letter D? At the top. Okay. And that just leaves B right over here. Okay. Now, if we assign the stereochemistry here, now we can. The direction we determined, that is the direction of whatever stereoisomer that will be. Okay? So what is it in this case?
Wait.
All right, so let's take a moment.
It's R.
It's R. All right, so if doing these directions in your mind, it can trip you up sometimes. So I would always just draw the lines, okay? Just so we're learning about this, all right? So A to B, B to C, C to D, okay? So that still is R, right? Letter R. So clockwise, R. Okay, are any questions about using Fisher projections? So that's a common way to draw a molecule with like lots of stereocenters. Yeah, Mariana.
I just have a question. On that last part, I thought we skipped over C. Like, where are you?
Oh, no. So that's when we rotate it. But remember, when we still assign stereoisomers, we still have to go in, we still have to follow like the top priority substituent, the second, and then the third priority. That's how we assign R and S. Yeah. But to your point, C didn't change, and that's because we rotated around it. But when we assign R and S, we're not rotating again. We're just following the order, the sequence of first, second, third, A, B, C. That tells us R or S. Okay. Are any other questions? Yes.
And then you can hold
Yes.
It can be any of them?
It could be any of them, as long as you just hold one in place. Yes, right. Okay. All right, so now we're going to talk about, we've been just talking about molecules with one stereocenter, but most of the molecules in the world, in nature, they have many stereocenters. So there could be situations like there's 10, 20, 50, okay? So it gets complicated really fast. So let's talk about when you have more than one, okay? So let me just hide this one, another layer here. All right, I'm working pretty nicely today. Okay, so what if we have more than one stereocenter? Our lives get a little bit more complicated, okay? So the key things to remember here is there's a nice equation you can use to know, all right, if I ask you, draw all the possible stereoisomers for 1,2-diethyl octane, okay, something like that. You might be like, all right, how do I know how many there are? Well, there's a formula we can use to write that, okay? And that's probably as advanced I will ask, okay? So let's talk about that. Molecules containing more than one chiral center. All right. So when you have this situation, you get another relationship between what we call stereoisomers. That's called diastereomers, okay? So DIA stereoisomers. So stereo, the position in space, okay? So, well, we have to draw many isomers here. So how do I know how many there are? Well, as opposed to structural isomers, where you really, you just kind of have to rearrange the bonds in many different ways as you can. In stereoisomers, there's a neat little equation, okay? So right now, I'll just give you this, and I'll kind of box it so you know what it is. So total number of stereoisomers all right, the equation is 2 to the power of n. All right. Does anyone have any idea what you think n stands for? Not number of carbons. So when we look at stereoisomers, what's the only difference? The reason we could write stereoisomers, right, is because in our molecule, one of the carbons is what? Chiral, right? So N stands for, what do you think? Chiral. Yeah, chiral centers, or number of stereocenters, right? Chiral carbon atoms, for our case mostly, because we're organic. So number of stereocenters. All right, so the reason why we draw 2 enantiomers for one chiral carbon is because when we put 1 into that equation, what do we get out? A 2 to the first power. 2, so there's only 2 enantiomers, right? So that's why there's only 2 enantiomers, okay? Now I have 2 chiral centers. How many total isomers, stereoisomers would you get? 4, okay? And that's probably as much I would ask you to write, 4, okay? And on an exam setting, because you have other stuff to also remember as well. All right? So I have 2 to the 1, so this will be for 1 chiral center. You're going to have 2 stereoisomers. So the only possible ways to draw this, both stereoisomers, they will be your enantiomers, the stuff we've been going over, the mirror images that we've been going over, okay? So these are enantiomers. All right, if there's 2 chiral centers, you get a total of 4. So far, sorry, this will be 2 chiral centers here. Four total stereoisomers. All right, so you actually get 2 pairs of enantiomers here. So you get 2 pairs of enantiomers. And we're also going to go over the other relationships as well. Okay, so there's also diastereomers, but we'll go over that relationship in the next section. Okay. All right, are there any questions about this equation? So this is the easy way to figure out how many stereoisomers you have. And I'll show you an example of what I expect for like what to draw, okay? All right, so let's go over our next example here. All right, so I'm going to draw, let me see, I probably have enough room. All right, so let's just draw like this. All right, so let's do an example here. All right, so I'm going to draw a Fisher projection. Now here, I'm going to have 2 chiral centers. So I'm going to have 2 intersecting points on my crisscross here. Okay, so let's make this the first group, the COOH. So that's carbon number 1. NH2 is right here. So we have an amine. Here's an H, an H, OH, and then CH3 right here. So let's number the carbon atoms, 2, 3, and 4. All right. So I will just say right away that the stereo centers here, I'm going to abbreviate, I'll put them in parentheses. At the 2 position is 2R. So it has the R center. And at 3, it's 3R. Okay? So, if we have time, we can go over one of them. But here you would have to rotate a few bonds here to get hydrogen on the vertical and then assign R and S. So if you want, please go on your own time, go ahead and verify that they are this. But for the purpose of this example, I'm just going to show you them, okay? So let's draw our mirror plane. So what would the mirror image, let's draw the mirror image here, okay? So if you know what the mirror image is like, go ahead and draw it. COO. All right. So when you have a mirror image, you don't have to assign R and S as long as you know the configurations for the first stereoisomer, the first enantiomer. Because what will if it's a mirror image and it's an enantiomer, what will the configuration be? Not the same. The opposite, right? It's like you have an image here and you do the mirror image. They're the same in every respect. They just have the opposite configuration around the chiral carbon. So what would I write here? Am I going to write 2R, 3R? 2S, 3S. Good. Okay. So look at here. I have 2 chiral centers. So how many stereoisomers should I draw? There should be 4 total, okay? So what we can do here is, all right, I'm going to write smaller here for this one, okay? So there's still a mirror plane here. All right, and the groups are the same. On the top and the bottom, the groups will be the same, okay? So the only thing we're going to change here is the groups on the horizontal, okay? All right, so, well, we can't draw the opposite configurations from the top and on the bottom because that will just give us the molecule we already drawn, okay? So what I want to do here at the 2 position, we're going to keep it the same orientation. So H and H2. All right. Well, what we're going to do to the dirt carbon? The dirt carbon, the second stereocenter, in order to get a different stereoisomer, what should we do here? Flip them. Good. The answer I was looking for. All right. So this configuration now. Well, at the second carbon, did we change anything? Sorry, let me just write the second carbon here. 1, 2, 3, 4. At the second carbon, did we flip anything? No, so carbon 2 will stay the same. So that's 2R. Okay. But what did we do at the third carbon? We switched it. So we made it to the S configuration. Good. All right. Now to draw the last one, you can be like, oh, wait. Now if I just draw the mirror image of this one, that will be a different isomer because one has not changed. So if I draw the enantiomer of that, or the mirror image, I'll get the last stereoisomer. So this is going to be our mirror image again. So H, H2N, and this one, HO. No, sorry, not HO. H, OH, right there. All right. So what will be the labels for these stereocenters? 2S, 3R. Because remember, these right here, the relationship between these two molecules here, all right, an enantiomer. I'm going to abbreviate it. All right, now I'm going to draw a series of arrows, okay? So let's see if we, oh, wait, did I say, let's see. Okay. Did I? Nope, okay. All right, enantiomers. What we can say about enantiomers, the stereocenters, they change, okay? Now, if you have two stereoisomers and one of them changes and one of them changes, what do we call that? So they can't be enantiomers, right? Because they didn't change. So what's the other term we write for enantiomers instead? Diastereomers. So look at these two examples. So I'm going to draw a bunch of arrows, okay? So the relationship between these two and these two, what do you think it is? Are they enantiomers? If we go from one diagonal arrow, those two structures, are those enantiomers? No. No. So the diagonal ones, they are diastereomers. So don't know where to put this. Let's just write it right here. Oops, sorry. Those are diastereomers. Okay. Oh, what about these two? Let's compare these two now. What are these two? Enantiomers or diastereomers? Yep, diastereomers. All right. Now there's one relationship we haven't considered. Which one is that? The top two, what are these called? Yep. All right, so the takeaway is, for two carbon centers, if there's no, all right, for now, there are 2 pairs of enantiomers and there are 4 pairs of diastereomers. You don't have to label like all of them, but you should really take away here that they're all different from each other, and that's why there's 4 of them. Okay, so diastereomers. So let's just state right here enantiomers. Oops, sorry. They are mirror images. All right, they're mirror images. Okay, and then what can we say here? That the chiral centers change. Okay, so they switch. They swap configuration between mirror images. All right. What do we think about diastereomers? Are they mirror images? No. So they're not mirror images. They're not superimposable. All right. And the only difference here is that between diastereomers, at least one stereocenter is the same. That's the definition. At least one. All right. So not all the stereocenters switch from one mirror image to the other. That's the definition. All right. So let's put here diastereomers. They are not mirror images. Okay, and one stereo. Let me just do chiral center. One chiral center does not change. And we can see that for each of these examples. For the one on the right, top and bottom, the stereocenter at position 3 change, 2 stay constant, okay? And the ones on the diagonals, the ones going from left to the bottom right, the second stereocenter changed, but the third didn't. And the other diagonal there, 3s is the same, but 2 changed. And then for the left, the diastereomers from top to bottom, 2 stayed the same, but 3 changed. Okay? So you see here, all these configurations, they have different combinations, so they're in fact all different. Okay? And that adds to the layer of complexity of separating all these out to have a pure compound. All right, are any questions on diastereomers? Do you want to go over another example? Any clarifying questions?
Can we do another example?
Yes. All right. So let's do. Let me see here. Let's draw the stereo isomers of, all right, 1, 2, let's see if this will work, difluoro butane. All right, let's see if this works. Let's draw our butane. All right. Actually, let's not do this one. Sorry, guys. Let's make this a pentane. Because there's a situation I don't want to talk about yet. That we'll talk about later. So pentane, let's change that to pentane. Okay. Yeah, my bad. We should make it 2,3. Sorry about that. Okay. So there's 4 ways we could write this, right? So let's make them both wedged. All right. What's another way we could write 2,3 difluoro butane. Dash, yes. Okay, good. And then what's the other way? So remember, there's two stereocenters here, right? Where are the stereocenters? Right here, right here. Right, because one of them is H, right? So we have an H coming off right here, H coming off right here. And the other groups are a methyl, and the other group has the other fluorine on a carbon, and vice versa. We have an ethyl in the other direction for the second stereoisomer. Okay, so, but we drew two of them, right? There's two chiral centers, so how many stereoisomers can we draw? 4. So let's draw the other two. So, now how do I draw the other two? Yes, right. So we're going to change, maybe let's change this one, right? Change this one to dash instead. And this will be wedged. And then the last one, what would we do there? We just swap it backwards, right? Change the other group instead. So you might be asking me, wait, Andrew, what we just flip it on itself? Wouldn't it just be on just one of these other ones? You should try and do that. So you try and flip it, right? If you flip one of these, what's going to happen to the wedge and dash bonds? They're going to swap, and your orientation is going to be backwards, right? You're going to go, it's like the mirror image. You're going to get the opposite, okay? So now let's go ahead and assign the stereocenters, okay? Because that's something you probably will have to do just to make sure, right? Oh, what's this stereocenter? If I ask you to draw them, though, I probably won't make you do that. But you got to be sure. I'll double check just to make sure that, oh, these are the correct stereoisomers, okay? Based on the R and S. So let's do the first one together. All right. After, let's take like 5 minutes. How about you guys pair up and talk about it, and I'll check back after 5 minutes, and we'll go over them together, okay? All right. Here's some talking. Assign R and S to each of these structures, okay? Just so we can identify that they're all there. They're all there. Yeah, at the 2 and 3 position, you want R and S. So guys, you want to assign R and S to the second and third carbons of each of these structures. Okay, just to be clear.
So more hydrogen, lower pH. This priority fluorine, but also, and then next one would be
Well, this is just two, I'm just. So, it goes to the page is always. We have our smallest worker rate.
So if this is I think yeah. Okay, so then the
So then that would be. So they're not very no, because that's like okay, so right here, yeah, so like it's like diastereomer, which makes you feel no, they don't. That's why it's just one variant. This is whereas an enantiomer, both of them change. So this one's super cool. Correct. So, but one get back and because this only has protein, because there's a tie, because we both have that. This one has one S. This would be primary, higher company. This would be C. This would be C2, and that carbon. So this would be also S. Going I feel okay, but I watched the videos this morning, specifically on this.
I just like put it on and sit there and
Yes. Huh? A long one? No. Alright, you guys, let's go over it. Okay, so what do we get for the first one? Any ideas? 2. Alright. So let's number these there. 1. Alright, what we get for number this first one? 2 what? I got R. Anyone not get R? Okay, so maybe the priorities are mixed up or flipped up. So check that. So which one should have first priority? F. Fluorine, and then which one?
then the carbon has the other fluorine attached to it.
Right, and then lastly, where's C at? The methyl group. And hydrogen gets D right here. So we go from A to B to C, we get R. Okay. Well, for this one, isn't this the same thing? 2R. Okay. How about the third carbon? What was that one? S, right? Because look at the B group now is directly on the other side for this stereocenter. So for this one right here, let's look at this one. 3, it should be S. So we're going from A to B to C. Wait a second, is it? Is it? I don't know. Let's see. Is it R? There's a different color I could do. Let's try that. A. Well, I guess that didn't work. A. Let's do A1. B1. And then C1. All right. All right. Still clockwise, isn't it?
Yep.
So 3R. All right, guys. If we didn't get 2R, 3R, let's see where we went wrong. It might have been we just labeled some of the letters incorrectly. So it's helpful to do lots of practice. Okay. Well, now that we have these, did you guys end up assigning the rest of these, or did you see a connection here? Well, if it's a dash bond, isn't that like switching the H and the hydrogen? So that would create your enantiomer. So what would be the configuration for this one? Yeah. This one still has 3R, right? But it's 2S because I went from dash to wedged, okay? So when you switch to wedge and dash bond, that's also how you change the enantiomer, okay? Because let me just show you this. All right, let me show you this. Okay, if I drew the mirror image of this, right, what will I get? this right here. Will this be the same as the mirror image? Do we all agree that's the mirror image? All right, but if we flip this molecule over itself, what happens to these wedge bonds? So let's rotate. So let's rotate this. So we're going to rotate over this axis. So let's rotate here. So let's rotate vertically. What's going to happen to these wedge bonds? They're going to go back to dash, yeah. See? That's why I wrote it that way. So the mirror image is actually the dash form in the same relative orientation here. That's another trick you can use. Okay? So let's finish up this one. So we see here the ones in the first row, they're enantiomers. And now the second row, they should also they should also be enantiomers. Wait, this should be 2S, shouldn't it?
Yes.
My bad. I was confusing myself. Okay, there. 2S, 3R. Okay. Then what's this last one here? 2R, 3S. And are they all different? That's it. Okay. All right. So let's go over just a few more things, and then we'll take a little break, okay, before the quiz. All right? So one thing we have to talk about now is Meso compounds. So we didn't really talk about that in much detail on the lab, but I'll show you what it means right now, okay? Yeah, it's called Meso. No, it's not miso soup. Okay? I heard that joke before. All right, if you have any question about this, don't feel afraid to reach out, okay? I know it's tricky stuff. It's not easy. All right. So we pronounce it Meso. Okay. So these compounds, you have two chiral centers, but it turns out one of them is achiral. Okay? So it's achiral compounds containing stereocenters. All right. So we can say here two molecules are identical because there is a plane of symmetry. So if there's a plane of symmetry in the molecule, these molecules are superimposable and they're no longer chiral. All right, so that's something we'll have to be able to identify. Okay, there's a plane of symmetry, and this compound is achiral. All right, let me give you an example. So you notice this if they're in the same orientation, like we saw in lab. Okay, so here you have, it looks like you have stereocenters, but the unique thing about this happens when you have the same three groups on both stereocenters. Okay, the same three groups. Okay, so here, HO, H. Okay. Now, if we draw the mirror image, right, the mirror image would be this. But what's unique about this? Look at the stereocenter. So the first one, 2s, 3r. 1, 2, 3, 4. 1, 2, 3, 4. It looks like they have stereocenters, right? They have chiral centers, but because of a symmetry element here, they are not chiral. So where is the mirror plane in this molecule? Is it vertical? Do we go vertically through the molecule or horizontally down the center? Yep, horizontally. So if you draw this mirror point here, oh, sorry. Okay, so these right here is the mirror plane. So these molecules are actually the same molecule. They're the same thing. So you actually only have 3 stereoisomers, even though you have 2 stereocenters. And that's because one of them is a meso compound. They're the same exact molecule. All right, that's pretty much all I want to say about this. But I'm going to, we're going to talk this about one more thing, okay? And then that'll be it for stereochemistry, okay? But are any questions about this meso compound? So the one you have to recognize here is that, do you have a meso compound? And if you do you expect it to have optical activity or not? Okay? That's the things I would consider. All right, so let's, this won't take too long. The last thing I'll mention about stereochemistry and how it applies to what we do going forward, chemical reactions, okay? So, are there any questions on this page? No? All right, so hang in there, okay? I know there's a lot of information every day, okay? So, last thing, stereochemistry. Of reactions. All right, so what happens when we create stereocenter? Things get complicated, okay? So remember this reaction. What would the product of this reaction be? If I only do one substitution of bromine, where would the bromine go? The first carbon or the second one? The second one. Remember the relative reactivities? Bromine will always choose the more substituted carbon atom, and that's the internal one. Good. All right, so I like to indicate a new chiral center by putting an asterisk. So that's our new chiral center because now it has bromine attached and then an ethyl group right here. All right, so there's a problem with radical reactions. They're not what we say stereospecific. It doesn't prefer one isomer over the other. All right, so let's revisit the steps for bromination. All right, what happens in the first step here? It breaks. So remember, it breaks. So this is called homolytic cleavage. So it breaks, the electrons break evenly to both atoms. So 1 electron each from the bond. And we get 2 Br atoms, okay? Then the bromine atom is going to do, to do what to this? To this the main molecule here. All right, you guys remember? What happens here? Yes, so at the secondary carbon is going to cleave off an H. So it's going to cleave it like so. 1 electron each, so you should draw 3 arrows to indicate that another radical is being formed. But what's the byproduct? What also forms here? HBr. So remember, when you these arrows, they're transferring one electron each, bringing one electron in, you form a covalent bond, right? So HBr. All right, so now this is where it gets tricky, right? This is now where we take our radical here. Okay, so this is something I wanted to show you. The radical is not in a hybrid orbital. So when we broke that bond, the radical is now planar. It's an sp2 type situation. So in an sp2 type, we have a free what? No, not carbon. What orbital? What atomic orbital is free in an sp2 hybridized molecule? The p orbital. So it lives in the p orbital. Well, don't we remember the p orbital, right? It has a top lobe, and what else? What's the other lobe? The other bottom lobe, right? So this actually can go in two directions. You have Br attacking from the top face to give you, so this, if we do the assignments here, this is the S isomer. All right. What do you think happens when we talk from the bottom? So this can also attack. So remember the electron in the p orbital, it could be in the top lobe or it could be in the bottom lobe. So it can actually attack from the top face. So this is what we call the top face, okay, of the p orbital. This is the bottom face of the p orbital. Okay, so now the Br can also attack from this region right here. So if the electron was, say, right here, it can also attack there. All right. But instead of drawing the bromine upwards, we're going to position the bromine in what direction? Yeah, downwards, coming from the bottom. And now if we assign the stereoisomer here, this is R. 2 bromo butane. Okay, and then what comes out of here in both steps is a Br radical. So what ratio do you have? Well, it depends, but in this case we get a racemic mixture. Okay, you got equal opportunity for both products, so that'll be racemic. All right, so that's how stereochemistry plays a role in chemical reactions, and we'll see more of stuff like this down the road, okay? All right, so let's take 5 minutes. 5-minute break, come back, take quiz. All right, everyone sign in attendance. Please remember to sign in.
Either. Yeah.